6-for day 4. Our objective for today is this. Know when a special differentiation procedure called logarithmic differentiation must be used to find the derivative of a function and how to do this. So when do we have to use this special differentiation procedure and how do we use it? That's what we want to learn today. So let's take a look at our notes here for today. The main idea is this. This is the main idea having to do with our learning objective for today. And to help you understand this main idea, we're going to look at these 5 functions that we have here. The first 4 are in one category, and the last one is in a separate category. So when you look at the first function, we have y is equal to e. Now remember, e is a constant. It is approximately 2.7. So it's just a constant. It's like having y is equal to 3, but instead of 3 we have e, or for example y is equal to pi. Pi is just a constant. It's about 3.14. So the first function is a constant function. Do we know how to take the derivative of a constant function? Yes. The derivative of a constant function is 0. So for the first function, the derivative would be 0. Now look at the second function. The second function is y is equal to e to the x. It's the natural exponential function. We know how to take the derivative of the natural exponential function. It is itself. Now look at the third function. The third function is y is equal to x raised to the e power. Now, e is just a constant. It's about 2.7. Now look at the fourth function. Y is equal to x squared. So both of these functions are what we call power functions. You have powers in which the base is a function of x and the power, or the exponent is a constant. How do you find the derivative of a power function? You use the power rule. And before we find the derivative of each function, let's quickly distinguish the difference between a power function and an exponential function. In an exponential function such as y is equal to e to the x, you have a power. The base is a constant, but the exponent is a variable. In a power function, you have a power. The base is a variable, but the exponent is a constant. So now let's take a look at these 2 power functions that we have and how to find the derivative of each one. We'll begin with this one because you can probably understand that more easily. So we have y is equal to x squared. So using the power rule, you just bring the exponent to the front and you have 2x to the first power. Subtract 1 from the exponent. So you would do the same thing for this function. You would bring the exponent to the front and you'll have e, and then you'll subtract 1 from the exponent, so you'll have x to the e minus 1. So now we know how to find the derivatives of all of these 4 functions. How is the 5th one different from the 4 that we've looked at before? The 4 that we just looked at. So this is the 5th function. We have y is equal to x to the sine x. Let's compare it to the 4th function, y is equal to x squared, and the 2nd function, y is equal to e to the x. We said earlier that the 4th function is a power function. In the power, it is the base, that is, in this case x, or generally a function of x, and the exponent is a constant. And in the 2nd function, we have an exponential function. In the power, the base is a constant, and the exponent is either x or a function of x. But look at the 5th function. Look at this one that we have here. You have a power, but it's different from both an exponential function and a power function in this way. Both the base and the exponent are either x or a function of x. So you cannot use the power rule to find the derivative of this function like we did for the power function y is equal to x squared. You cannot use an exponential differentiation rule like we did for the second function because this is not an exponential function. So how do we find the derivative of such a function as y is equal to x raised to the sine x? We have to use a special differentiation procedure called logarithmic differentiation. Now we know when we have to use it, when we have a function and we have a power and both the base and the exponent are functions of x, we have to find the derivative by using this special procedure called logarithmic differentiation. And now we'll take a look at how this is to be done. So I'll show you how to find the derivative of y is equal to x raised to the sine x power. And the main steps in this process called logarithmic differentiation are: 1. Take the natural log of both sides of the equation. Use properties of logarithms. Use implicit differentiation. So let's take a look at that. So here's our function. We'll begin by taking the natural log of both sides of the equation. So there's our first step. Take the natural log of both sides of the equation. Now we're going to use a property of logarithms. This is called the power property. And we can use that to bring this exponent of sine x to the front here. So we just did that. And now we're going to take the derivative of both sides of this equation with respect to x. So I'm setting up for that. And before I go any further, I'd like to make a couple of notes. On the right side, you'll observe that we have a product of two differentiable functions. So on the right side of the equation, we will have to use the product rule. On the left side of the equation, you'll observe that we're taking the derivative with respect to x, but our function is natural log of y. So we will assume that y is some differentiable function of x. And therefore we will use implicit differentiation. We will use the chain rule. So this is what we have. On the left side, we take the derivative of the outside function, which is natural log. The derivative of natural log is 1 over the argument. The argument here is y, so we have 1 over y. And then we use the chain rule. This is called implicit differentiation. We now multiply by the derivative with respect to x of the inside function. The inside function is y, so we have the derivative with respect to x of y. On the right side, we have the derivative of sine x times natural log of x. We use the product rule, the derivative of the first function times the second plus the first function times the derivative of the second. So this is the last line from the previous slide, and now we're just going to continue. So here is what we have. We have 1 over y, and the derivative of y with respect to x is dy dx. The derivative of sine x is cosine x times natural log of x plus sine x times the derivative of natural log of x is 1 over x. Now we're going to simplify just a little bit. So all I did was I multiplied the sine x times 1 over x to get sine x over x. And now, what is it that we want to find in this problem? We want to find the derivative of the function. We want to find dy dx. So we're almost there. We just have to isolate it on the left side. And the way we can do that is by multiplying both sides of the equation by y. Because when you multiply the left side of the equation by y, 1 over y times y is 1. So now you just multiply the right side of the equation by y, and we will have dy dx, isolated on the left side. So this is what we have. The last thing that we can do is replace y with what y is. So this is our function y that we began with. So we can replace y with x raised to the sine x power. And we have found the derivative of our function. It is right here. So we just looked at an example of a procedure called logarithmic differentiation. We began by taking the natural log of both sides of the equation. we used a property of logarithms, and then we used implicit differentiation. So here is example 3 from the book as another example. We want to find the derivative of the function f of x is equal to x to the third plus 4 raised to the cosine of x. Again, this is the type of function that you need to use logarithmic differentiation for. We have a power in which both the base and the exponent are functions of x. So how do we begin? We begin by taking the natural log of both sides. So that's what we see here. If you want, you can replace the f of x with y, or you can leave it as f of x as we have in the example. So take the natural log of both sides of the equation. The next step is to use a property of logarithms, the natural log of a power property, to rewrite the right side of the equation. So here's the natural log of a power property. So what we need to do is we need to take this exponent of cosine x and bring it to the front. So we have cosine x times the natural log of x cubed plus 4. Now we're ready to differentiate both sides of the equation with respect to x. So I'll just show a couple of extra lines to help you understand how we go from here to here. So we're taking the derivative of both sides of the equation with respect to x. How do you find the derivative of the natural log function? It's 1 over the argument, but then you have to use implicit differentiation because here you have an inside function. You have to use the chain rule. And on the right side of the equation, you have to use the product rule. So the derivative of the first function times the second plus the first function times the derivative of the second. And when we do that, this is what we get. So let's look at the left side. We have 1 over f of x times the derivative with respect to x of f of x is f prime of x. And of course, that's what we're looking for in this problem, so we'll have to solve for it in the next line. On the right side, we have the derivative of cosine of x with respect to x is negative sine x multiplied by the natural log of x cubed plus 4 plus cosine x times the derivative with respect to x of natural log of x cubed plus 4. And how is it that we get 3x squared over x cubed plus 4 from the derivative with respect to x of the natural log of x cubed plus 4? Let's take a look at that. So you'll observe that we have a composition of two functions. The inside function is x cubed plus 4. The outside function is natural log. So to take the derivative here, you need to use the chain rule. Take the derivative of the outside function, evaluate it at the inside function. The derivative of the natural log function is 1 over the argument, and then multiply by the derivative with respect to x of the inside function, x cubed plus 4. And the derivative of the inside function is 3x squared. So that's how you get the derivative 3x squared divided by x cubed plus 4. Now we're ready to solve for what we want, which is f prime of x. So all we have to do is isolate f prime of x in this equation by multiplying both sides of our equation by f of x. And when we do that on the left side, what happens is f of x will cancel with f of x, and we're isolating the derivative. And on the right side, we'll have what we had from the previous line, which is right here, and multiply that by f of x. But of course, f of x is x cubed plus 4 raised to the cosine x power. And there's our final answer right here. Here's example 4. In the previous two examples, we had functions where we had to differentiate using the new procedure that we're learning today called logarithmic differentiation. In this example, we don't have to use logarithmic differentiation to find the derivative. Instead, we could use something called the quotient rule. However, this problem could also be done by using logarithmic differentiation, and we'll see if this is perhaps easier to do than trying to do it using the quotient rule. I'll go through the example as it is done in the book, where we go through logarithmic differentiation to find the derivative, and afterwards, if you'd like to try the quotient rule on your own to see how it compares as far as the level of difficulty, you can do that. So if you wanted to do this problem using logarithmic differentiation, you would begin by taking the natural log of both sides. You would then use properties of logarithms and then differentiate implicitly. So here we begin by taking the natural log of the left side and the natural log of the right side. And here's the key step that you need to understand. I am not going to differentiate right now. Instead, I'd like to simplify the expression that I have on the right side of the equation using the properties of logarithms, and then it will become easier for me to differentiate the right side of the equation. So we're going to use these two properties of logarithms. The first is called the natural log of a quotient property, and the second one is called the natural log of a power property. And let's see how we use those two properties of logarithms to expand the logarithmic expression on the right side of the equation. So first we use the natural log of a quotient property. If you have the natural log of a quotient a over b, you can write that as the natural log of the numerator minus the natural log of the denominator. And that's what we're going to do here. We have the natural log of a quotient, so we're going to write that as the natural log of the numerator minus the natural log of the denominator. The next thing that we want to recognize is this. Here we have the natural log of the cube root of x plus 2. You can write that as the natural log of x plus 2 to the 1/3 power. And that will set us up for using the next property of logarithms, the natural log of a power, to further expand each of our two logarithmic expressions before differentiating. So in this first expression, you can use the natural log of a power and bring the exponent 5 to the front. So we have 5 times the natural log of 3x plus 7. And then we have the minus sign. And we're going to go ahead and use the natural log of a power to go ahead and expand this expression here. And we can take this exponent of 1/3 and write it out front. And then we have times the natural log of x plus 2. So up to this point, I haven't done any differentiation. All we've done is we began by taking the natural log of both sides, and we used properties of logarithms to expand the expression on the right side of the equation. And now we're going to differentiate both sides of the equation, and let's see what we do for that. So on the left side of the equation, we're going to use implicit differentiation. We have a composition of two functions. The inside function is f of x. The outside function is natural log. So the derivative of the outside function is 1 over the argument. So we have 1 over f of x. And then multiply that by the derivative of the inside function with respect to x. That's implicit differentiation, the chain rule. And we have f prime of x. So now I'll explain how we get 15 over 3x plus 7. That is the derivative of 5 times the natural log of 3x plus 7. So here you have a constant multiple, so you can take that out. And then here you have a composition of two functions, so you have to use the chain rule. The derivative of the natural log function is 1 over the argument, and then multiply by the derivative of the inside function, 3x plus 7, which is 3. 5 times 3 is going to give you 15 over 3x plus 7. So that's how we get that. How do we get this? It is the derivative of 1/3 times the natural log of x plus 2. And of course, the minus sign here is carried over here. So the 1/3 is a constant multiple, so you can take it out, factor it out, and then the derivative of natural log is 1 over the argument. Multiply that by the derivative of the inside function x plus 2, which is just 1. So this is what you get. Now 1/3 times 1 over x plus 2 can be written in the form that's shown here in your textbook, where you have 1/3 in the numerator over x plus 2 in the denominator. So again, what was it that we wanted to find to begin with? F prime of x. Now we can find it because we have f prime of x here. So to find f prime of x, I just have to multiply both sides of our equation by f of x. And when I do that, f of x, when I multiply by f of x on the left side of the equation, it will cancel with the 1 over f of x, leaving me with f prime of x on the left side of the equation. And on the right side of the equation, I'll have the work from my previous step. Multiply that by f of x. What is f of x? Right here. That's f of x, so I just write that in for f of x, and there's my answer. So this was an example in which we did not have to do logarithmic differentiation, but we could have done it, and we did do it. You can alternatively find the derivative for this particular example by using the quotient rule. But we learned today that there are certain types of functions where you have to use logarithmic differentiation. If you have a power and both the base and the exponent are either x or functions of x, you have to use logarithmic differentiation to find the derivative of such a function. How do you do logarithmic differentiation? Take the natural log of both sides, use properties of logarithms, and differentiate implicitly with respect to x.